Okay, picture this. There's this invisible battle, right? Happening constantly inside all of us. These tiny invaders, viruses, they sneak into our cells. And then they basically turn them into little virus factories. For the longest time, figuring out how to fight these guys without, hurting ourselves, it felt almost impossible. So today we're doing a deep dive into the really fascinating world of antiviral agents. Our mission basically is to unpack how these special meds work, which viruses they go after, and the unique challenges involved. We're using a great chapter on antiviral agents from our sources, really getting into the nitty-gritty. And by the end, you'll have a much clearer picture of why viruses are so darn tricky and the clever ways science is fighting back. No getting bogged down in jargon, promise. Let's get into it.
It really is quite the challenge. I mean, the basic problem with treating viruses, it comes down to one thing. They can't replicate on their own. Totally different from bacteria. Bacteria can just multiply by themselves.
Ah, right. So it's not like they're self-sufficient. They actually need us. Our sources really stress that point. A virus has to latch onto and get inside a host cell first.
Exactly.
And once it's in there, it doesn't have its own power source. It just hijacks our cells' energy, our machinery, to make its own stuff, proteins, DNA, RNA. It's like a tiny squatter taking over your entire workshop.
That's the core issue, precisely. Viruses live inside our own cells. They're embedded in our machinery. So any drug that's strong enough to kill the virus, well, it runs a serious risk of harming our own healthy cells too. Our source material puts it bluntly. Treatment of a viral infection is difficult without serious toxic effects for the host. It's this incredibly fine line to walk.
Wow, it sounds like fighting an enemy that's hiding among your own people. But okay, despite that huge hurdle, science has developed treatments. I was actually surprised by the list in our sources, the range of viruses that antivirals can tackle now.
Oh yeah, it's pretty broad. We're talking common stuff like influenza A, some other respiratory viruses. Then you got the herpes viruses, cytomegalovirus, CMV, people often call it. But also, really major global health issues like HIV, the virus that causes AIDS, and hepatitis B and C, and even some viruses that cause things like warts or certain eye infections. It shows how far we've come, really.
Yeah, that's quite a list. And given how viruses work needing our cells, it makes total sense that the drugs have to be super specialized. Definitely not a one-size-fits-all situation. So how did these different classes of antivirals actually zero in on such sneaky targets?
Well, okay, let's start with the ones for influenza A and some of those other respiratory viruses. Their main trick is pretty clever. They basically stop the virus from taking off its coat once it gets inside the cell. It's called uncoating. Think of it like jamming the zipper on a suitcase. The virus gets in, but it can't open up to release its genetic material. So it can't replicate, can't spread.
Ah, okay. So blocking a really early critical step. And what about how these flu drugs move through the body? Anything stand out there in the sources?
For the most part, they get absorbed pretty easily after you take them. They do their job, and then the body mostly gets rid of them through urine, often without changing them much. Of course, there are precautions. Like a lot of meds, you need to be careful if you have kidney issues or if you're pregnant or breastfeeding. Standard stuff, mostly. And side effects are usually things like, dizziness, maybe some nausea, but generally manageable.
Okay. Now, what about the drugs for herpes and CMV? Those are pretty common infections. Their mechanism sounds quite ingenious. How do they work?
Yeah, these ones are fascinating. They work by messing with the virus's DNA replication. They're like imposters. They pretend to be the building blocks the virus needs to copy its DNA. But when the virus tries to use these fake blocks, the DNA chains end up too short, or just wrong. They don't work. It basically jams up the whole replication machine. It's like trying to build something important with faulty parts. The whole thing just falls apart.
Faulty Lego bricks. I like that. A real spanner in the works for the virus's DNA factory. So what are the key things our sources flag about using these specific antivirals? Anything listeners should really know?
Well, besides the usual allergy concerns, a really big point is their potential toxicity in pregnancy and breastfeeding. That's a major flag. Kidney disease is also a factor in how the body handles them. And yeah, while you might get nausea or headaches, some potentially more serious side effects can include things like tingling or numbness, that's paresthesias, or even nerve issues, neuropathy. But maybe the most crucial takeaway, the really practical advice from the sources, it's about timing. For something like herpes simplex, the sources say, start taking the medicine as soon as possible to improve effectiveness of antiviral activity. Getting it early makes a huge difference.
Right, hitting it hard and fast. Okay, let's shift gears to HIV, the virus behind AIDS. This fight sounds especially complex. You often hear about a cocktail of drugs, multiple strategies. Our sources listed, what, 6 different classes of agents? Why so many?
Yeah, HIV is notoriously tricky. It's incredibly adaptable, mutates easily. So to really keep it under control, scientists develop these different classes, 6 main ones, and each one attacks a different specific step in the virus's life cycle. It's like a coordinated assault, hitting it from multiple angles at once. That's what's really turned HIV from, a near certain death sentence into something people can manage long term.
That's just incredible progress. Okay, let's briefly touch on some of these classes. What about the non-nucleoside reverse transcriptase inhibitors, the NNRTIs?
Right, NNRTIs. These are pretty direct. They bind right onto a key enzyme. HIV uses reverse transcriptase. This enzyme is what HIV needs to turn its RNA into DNA, which is essential for it to replicate in our cells. The NNRTIs just block that enzyme's activity. They get absorbed pretty fast, processed in the liver. Side effects can include GI issues, dizziness, sometimes point rashes can pop up. And importantly, some specific drugs in this class can interact badly with other meds, like certain heart rhythm drugs or sedatives. Doctors need to watch out for that.
Okay, direct hit. Then there are the nucleoside reverse transcriptase inhibitors, NRTIs. How are they different?
So NRTIs are more like decoys or imposters, similar to the herpes drugs we discussed. They look like the natural building blocks the virus needs for that same reverse transcriptase enzyme to build the DNA chain. The enzyme mistakenly grabs the NRTI instead of the real thing, and that stops the DNA chain from getting any longer. Process halted. Most are absorbed well, usually leave via the kidneys, but they can sometimes cause issues like bone marrow suppression affecting blood cells or, less commonly, problems with the liver or pancreas.
Got it. Decoys versus direct binding. What about protease inhibitors? What's their role?
Protease inhibitors target a later stage. After HIV makes copies of its parts, it needs an enzyme called protease to act like scissors. It cuts long protein chains into the right sizes to assemble new functional virus particles. Protease inhibitors block those scissors. So the new virus particles can't be assembled correctly. They're immature and non-infectious. They're generally absorbed well, processed by the liver. Side effects can include the usual GI stuff, but interestingly, they can also mess with cholesterol and triglyceride levels. So that means long-term monitoring of heart health becomes really important for patients on these. Adds another layer.
Right, blocking the assembly line. Then there are fusion inhibitors. The name suggests they stop the virus from even getting in.
Exactly. They block the very first step, the fusion of the virus with our cell membrane. If it can't fuse, it can't get inside to begin with. It's like locking the main gate. Now, unlike most of the others, which are pills, these are given by injection, under the skin. And because they're injected, a really characteristic side effect our sources highlight is injection site reactions. Pain, redness, lumps where the shot goes in. In fact, the source notes that if someone's reporting acute pain related to site reaction of the drugs, odds are they might be on a fusion inhibitor.
That's a key identifier. Okay, moving on. CCR5 core receptor antagonists, they also work on entry, don't they?
They do, yeah, but slightly differently. Think of the cell having different door handles or receptors. HIV often needs to grab onto one called CCR5 to help it get in. These drugs block that specific CCR5 handle. So even to the virus approaches, it can't get the right grip to enter the cell. These are pills, absorbed well, processed by the liver, and mostly leave through feces. Notable side effects can include dizziness, sometimes changes in consciousness.
Okay, another way to lock the door. And finally, in the HIV toolkit, integrase inhibitors. What unique step do they hit?
Integrase inhibitors block another crucial enzyme, integrase. Once the virus converts its RNA to DNA inside our cell, integrase is the enzyme that inserts that viral DNA into our own host cell DNA. It basically stitches it right in. By blocking integrase, the viral DNA can't become a permanent part of our cell's blueprint, which is obviously a huge step in stopping long-term infection and replication. These are also pills, processed by the liver. One thing to watch for, though rare, is a risk of muscle problems, like rhabdomyolysis.
Wow, okay. That's an impressive arsenal just for HIV. But the antiviral world extends beyond that, right? What about hepatitis?
Yeah, definitely. For hepatitis B, there are agents that work quite similarly to some of the HIV drugs we just talked about. They inhibit the reverse transcriptase enzyme specific to hep B, causing the DNA chain to terminate, stops replication. A key thing there is the risk of kidney toxicity, especially if taken alongside other drugs that are also tough on the kidneys, nephrotoxic drugs we call them.
Right, need to watch those drug combinations. And for hepatitis C?
For hep C, our sources mention that protease inhibitors, like the ones used for HIV, can also be effective. They're often used in combination therapy, maybe with ribavirin, or sometimes ribavirin plus peginterferon, especially for chronic cases.
Okay. Now, there was one more category mentioned, locally active antiviral agents. These sound different.
They are quite different, yeah. Their main thing is that they work right where you apply them, like a cream for a cold sore or drops for an eye infection. They interfere with the virus's replication or metabolism locally. But the crucial part, they are not absorbed systemically. They don't really get into your bloodstream or travel around your body. They just work on the surface, where the problem is.
That's a really important distinction. So side effects are mostly just local, too, like stinging or burning where you put it.
Exactly. Because they aren't circulating through your body, the main concern is just local irritation or maybe an allergy to the drug itself. It really minimizes those systemic side effects we see with the oral or injected drugs.
Okay, so we've covered a lot of ground here, from the basic problem of viruses hiding in our cells to all these really specific ways drugs target everything from the flu to HIV and hepatitis. It really gives you an appreciation for why getting treatment started early can be so vital and how complex managing side effects and drug interactions can be. And that difference between systemic and local action is key too.
Absolutely. It's a constant balancing act in medicine, fighting the invader without harming the host, especially when the invader is so intimately integrated with the host's own machinery. And viruses are always evolving too.
So thinking about this deep dive, what really stood out to you? Was it the cleverness of the drug mechanisms, the sheer number of viruses we can target now, or maybe that constant tightrope walk between fighting the virus and managing side effects?
That's a good question. For me, maybe it's the ingenuity behind targeting specific viral enzymes or processes. But to leave you with something to think about, our sources mentioned the different stages of virus replication. Now, every single drug class we talked about today, it zeroes in on one specific stage. So consider this. As we learn even more about the really intricate details of how viruses replicate, what new stages, what new vulnerabilities might we uncover? Could that lead to entirely new types of antiviral therapies down the road?